Şimdi Batu'nun sunumunu dinleyeceğiz. Batu, Boğaziçi Üniversitesi Fizik Bölümünde 4. sınıf. Aynı zamanda matematik bölümünde çift anadal yapıyor. Kendisiyle bence fizikteki en güzel fenomenlerden birisi olan integer kuantum Hall efekti çalıştık. Batu olabildiğince herkesin anlayabileceği bir sunum hazırlamaya çalıştı ama umarım matematik programında fizik sunumu yaparak Müslüman Mahallesi'nde salyangoz satıyor olmayız. Ben sözü Batu'ya bırakayım. Evet, buyur Batu.
Okay, today my talk will be about the integer quantum Hall effect and its relation to topology. So to give a brief outline, so I'll first give a brief overview of the integer quantum Hall effect and define some principal concepts. And then I'll introduce a concept called the Berry phase, which arises in some quantum mechanical systems. And this Berry phase is directly related to topology, we'll see. Then we'll define a formula named the Kubo formula to describe a type of conductivity I'll be introducing in the next slide. And we'll see how these concepts can be grouped together in an example, and we see the relationship to the topology. Okay, so to simply state, the quantum Hall effect occurs when we have a system of electrons in a 2D plate or plane, and we have a strong magnetic field. So in this talk, we'll assume the magnetic field is pointing upwards in the Z direction, upward Z direction. So here so this effect is first observed experimentally in 1980. And here we see a graph from the original paper. So we have the resistivity, the transverse resistivity, and the magnetic field. So we see there is an interesting relation between these two. So when we have the magnetic field in some specific intervals, we have a plateau of resistivity. So the resistivity don't change when the magnetic field is in this intervals, let's say. So the resistivities are quantized in a way. Okay, so to simply put, we have the Ohm's law, which relates the current density vector to the electric field vector, and they're related by a tensor named the conductivity tensor, and its inverse is the resistivity tensor. So it's a matrix. So the integer quantum Hall effect is a statement that this transverse conductivity, it takes on integer values. So this part is a constant. So E is the electric charge, H is the reduced Planck constant. So this quantity is quantized by an integer nu. So this nu is an integer. So this is the quantum Hall effect. And from experiments, we know that this nu is an integer. Okay, so let's talk briefly about the gauge invariance. So these are the Maxwell equations that governs all of the electrodynamics. So from this equation, which is called the Gauss's law for magnetism, we can define a vector potential for B. And it's defined as, so when we take the curl of this vector potential, we get the magnetic field. Because we have defined it as this way, we can actually choose A as we want it. So if we choose a specific A, let's say, the computations will be easier to compare to another selection of A. So one example of a magnetic vector potential, which we call a gauge, is the Landau gauge. So when we have magnetic fields is upward pointing, we can define A to be this value. So when we take the curl of it, we get this B. So this is called the Landau gauge. But yeah, we could have defined another gauges, but we'll use this one. Okay, so now a bit of quantum mechanics. So the quantum mechanics are governed by these two equations. These are the Schrödinger equations. One is for a time-dependent wave function, and one is for a time-independent wave function. So these are the partial differential equations. These two are, and the second one is actually a eigenvalue equation. So H hat is an operator. We call it the Hamiltonian operator, and we denote its eigenvalue as the energy. So this is the energy. And we also define the concept called a phase. It's a property of the wave function. Let's say this state vector. We call it the wave function, and the phase of a wave function, which is this complex exponential, has no effect on the measurement. So when we measure things, or let's say when we take the expectation value or the average of an operator A, the phase has no effect on the measured value. So we usually call these unphysical because it has no effects on the measurements. But sometimes we can measure these phase differences, and one example is the Baire phase, which I'll introduce. Okay, so what is the Baire phase? Suppose we have the Hamiltonian of this Schrödinger equation, and this Hamiltonian is related this Hamiltonian is a function of some external parameters. We call them lambda i's. So we are in control of these parameters. And what we do is we change these parameters slowly, and eventually we'll get them back to their starting values. So what we do is we let these parameters lambda I trace a closed loop in the parameter space. So when we do that, as we'll see, our system will take phase difference, and we call it the Baire phase. So we have a nice little theorem in quantum mechanics, and I'll just state it. It's called the adiabatic theorem. And its statement is that when we change this lambda I sufficiently slowly, the energy levels will not change. I mean, if we are, let's suppose we are in the n equals third energy state, we'll remain in the n equals third energy state when we change these variables quite slowly. And this theorem gives us the ansatz, so we can write our wave functions as a phase multiplied by a reference ground state, and these are all functions of time, because in time we'll be changing these parameters, lambda i's. So what we do is we want to solve for u, as we want to see what's the phase, and we assume that the ground state energy is 0. So we assume that our size in the ground state, and we say that the ground state energy, so this eigenvalue equation, H is an operator, so this eigenvalue equation in the ground state is 0. So this E0 is 0, we say. We set it to 0. And after some computations, we find the u to be this value, this exponential. Where in the way we've defined this funny AI, which is called the Baire connection. It is defined as this value. So what we want to do is we trace a closed loop in the parameter space. So what we do is we take our integral on a closed loop, and we get the beta phase, which is denoted as this value. And we can always use the higher dimensional Stokes theorem to make this integral a surface integral over the parameter space. So where we have defined this funny Fij, which is called the Berry curvature. And here is the interesting thing. So for any Berry curvature with an arbitrary number of external parameters, this integral over a closed surface is quantized by 2 pi c, where c is an integer, and this integer is called the Chern number. In mathematics, this is known as the Chern number, and this is a result of topology in mathematics. And we'll now relate this phenomenon to our quantum Hall effect, and we'll see how this quantizes the conductivity. Okay, so what we want is we want to have a formula for the transverse conductivity in terms of quantum mechanical observables. So we want to define a formula. So we call this the Kubo formula. So I think I should talk a bit about the perturbation theory first. Okay, so perturbation theory is when we know a solution to a problem, solution to this Schrodinger's equation in a case where we know the Hamiltonian and the state vectors or wave functions. So we know the solution of this H0, let's say, and when we make a small correction to it, we can approximate the solution containing this small value. So, and this is called the perturbation. So what we do is we introduce an electric field to our system. We have the 2D electron system with a magnetic field pointing upwards. We introduce an electric field as this. This is coming from the Maxwell's equations, and define our perturbation to be this. And we want to find this expectation value of J, or let's say the average current, due to this new perturbation, this small Hamiltonian, this is a small value. To do this, we'll work in the interaction picture of quantum mechanics, which states that any operator evolves in time as this with this equation, and any wave function is also evolving in time according to this equation. But these are not very, very important. Okay, so let me just say that when we have used these relations and we use an expansion in the wave, and we assume that, so let's state it like this. We have an electric field, we introduce an electric field in time, and when we have not introduced an electric field, we assume that the average current is 0. So this is our assumption. So when we have not introduced electric field, we take our current to be 0. So okay, after assuming this, we get a relation like this After opening the values, so we have just used J as a written J as a vector. So when we put here this I, Jx, okay, so first let me state that if the indices there are double of any indices, it means that there is a sum. This is called the Einstein summation. So there is a sum between these J indices. So let me just say that. So if you put this X here, and if you put y here, we actually get the relation between the current and the electric field. So this, when we put this here x and y, we actually get the transverse conductivity because we define it as the relation between J and E. And okay, we get the conductivity. Yeah, let's not dive too much into these computations. We use the closure relation in quantum mechanics, we integrate, and we expand this small denominator, and we get the Kubo formula in the end. So this is the thing we wanted. We wanted to state the transverse conductivity in terms of the quantum mechanical variables, which is their J, Y, Jx, and our energy levels, N and 0. Okay, so let's get to our example where we combine these concepts. So let's assume we have a rectangle with sides Lx and Ly. We identify the opposite sides, and let's assume we glue those together, and we actually get a torus. So we can assume that our system is a torus. Maybe a bit unphysical, but this is a good way to demonstrate the theorem or the relation to the topology. Okay, so here is our torus, and we introduce two fluxes to the system, this tube and this tube here. We can write those fluxes using the Stokes theorem. So if we have a magnetic field inside the solenoid like that, we can use this Stokes theorem to write the flux, which is this value in a closed line integral, and define the vector potential A. So because when we take the curl of A, we get B. We have defined A to be that way. And this dx term comes from our gauge. So in any time, the system has a magnetic field pointing upward. So we get this term here. And let's see. Okay, so we treat these added fluxes as a perturbation. And from the perturbation theory, the approximate new solution of the system is given as this. And when we calculate the dependence on the newly added fluxes, we get this. We just take the derivative, and this pi zeros now are ground states. And so we have the Kubo formula from before, and we can write these Browns and cap brackets and using these derivatives. So we get this equation for the conductivity. So now we do something peculiar. We introduce a dimensionless variable called the theta i's, like this. And these theta i's are in the range of 0 and 2 pi. So you may ask why this is in this range, but to explain this, we'll need to introduce another concept of spectral flow, but because of time troubles, I'll not go into that. So yeah, in terms of theta derivatives, we get this equation simply. So now we do a trick. So now what I'll do, I'll define a Berry connection over the system. So we added these fluxes phi x and phi y. So we can change these fluxes at will, because we introduced them. So we can also change thetas as we see fit. So we can define a Berry connection of the system. Then we can define a Berry curvature. And And we actually see that there's a very simple relation between these two. So when we compute a very curvature here, and we see that the from the Kubo formula, the conductivity is given as this value. So when we average over all fluxes, so when we take this value, this average, we write the same, nothing important. So what I mean by all fluxes, so we divide by 2 pi because we integrate over theta x and theta y, and they are both in the range 0 and 2 pi. And by the previous relation I've given to the topology, so yeah, this integral is over a closed surface. This integral is over a torus of parameters. So because the thetas are in the range of 0 and 2 pi. But we have previously seen that this integral, this part of the integral, is actually equal to an integer. And in this case, we name this integer as the first Chern number. And it's called the first Chern number because it's over a torus. And what we have actually done here is that we took a completely quantum mechanical quantity called the sigma xy, and we related it with a quantity called Chern number, where came from topology, and we have actually quantized our transverse conductivity here. So this was the story. So thank you for listening to me. Also, I'd like to thank the organizers of DRP Turkey and my mentor again.